My name is Alan Athanov and my work is about the watermarking method using radial point destiny for 3D model copyright protection. With the development of technology, the volume and complexity of 3D models have increased significantly, make them more appealing for copywriting, illegal use, and model substitution or modification. These threats can be prevented by watermarking, a special label embedded in the 3D model. It allows us to ensure copyright protection, authentication, and protection of models from modification. In this study, we consider a special kind of watermarking, zero watermarking. Its difference is that instead of modifying the model by embedding a special mark, we find unique characteristics of the model descriptors, which are robust to certain attacks. For 3D models, zero watermarking works as follows. For a protected model, we find a descriptor and save it in a database until we require it. When we need to verify authenticity of a model that may be corrupted, we recalculate the model descriptor and compare it with the saved descriptor in a database. If the values are equal or very similar, we can be confident that the model is ours. If the descriptor is very different, it means that it's a different model. Consider the method we have developed for calculating the descriptor, for which we require only the coordinates of model points. In the first step, we find the center of gravity of the model, after which we divide the region in which the model falls into n concentric spheres with a radius r for each sphere. The parameter n is user-defined. Next, all points of the model are distributed into n spheres according to their position in space. Finally, we divide the number of points in each sphere by the total number of points in the model and obtain the vector of destinies, which is the desired descriptor. To investigate the attack resistance of the descriptor, we will use the following metrics. Measure of descriptor robustness is defined as the average deviation between the descriptor difference of the original and distorted model. To estimate the average robustness to all distortions for different n, we find the average measure of robustness over all types of attacks with different parameters for several values of n. Also, to get the robustness threshold, we use a measure of the deviation between the descriptors of two different models and find its average value for whole dataset. For the experimental study, models from the ModelNet 40 dataset consisting of 40 different classes were used, from which two datasets were formed. The first consists of models differing in shape and size, and the second consists of models of the same class. Also, four standard models were selected for a detailed study of the influence of attacks on the descriptor. Armadillo, Happy Buddha, Stanford Bunny, and Dragon. The parameters of these models are presented in the table. To investigate the watermark robustness, we selected two types of vertex coordinate change attacks, including noise and model smoothing, and three geometric attacks, including rotation, shift, and resize. All these attacks were performed with different parameters as listed in the table. We conducted two experiments. The first one aims to find the most preferred descriptor length. For this purpose, we took a dataset of 100 different models and estimated the measure of deviation between one descriptors of all models for different values of n. The minimum, average, and the maximum deviation are depicted in the graphs. The robustness measure was also found for the armadillo model for different n. Its minimum, mean, and maximum values were plotted. Find the most preferred value of the descriptor length, we find the difference between mean upper delta and max lower delta, and the size for which the difference is the largest will take as the most preferred value. In this experiment, the best size of n is 17. It's also important to note that the one graph is higher than the other, so almost all values of n can be considered acceptable. Next, we perform a similar experiment using a dataset consisting of models of the same class. Here the results were slightly worse. The graphs overlap in some places, and the best size of n is 19. In the second experiment, we investigated the persistence of the descriptor as a function of attack strength for four different models. In this case, the result of the first experiment, 17, was taken as the descriptor size. The graphs depict the deviation of the descriptor value for the two types of noise and smoothing. As can be seen from the results, the deviation for almost all attacks is less than 1%, so the descriptor can be called robust to these attacks. It's also important to note that the descriptor has zero deviation for geometric attacks, so it is absolutely robust to them. In summary, the proposed method utilizing a descriptor based on zero watermarking technology presents a promising approach for safeguarding 3D models against diverse attacks. This method exhibits low sensitivity to noise in vertex coordinates, along with resistance to smoothing and geometric attacks. Furthermore, it was nothing that the computation of the descriptor is straightforward. It does not introduce distortions to the original model, and it demands only a minimal amount of memory. Thank you for your attention.